Welcome to ECE595, Statistics 598, or Machine Learning 1. This is lecture number 38 on conclusion. So to start with, I want to welcome you to the last lecture of the semester. It was a great experience discussing machine learning with you. In today's lecture, I want to go over two parts. The first part, I want to give you some practical advice of how are you going to debug your machine learning algorithm when you see some problems. The second half of the lecture, I want to give you some overall principles, 3 practical advices in designing your machine learning algorithm. One is the Occam's razor, the other one is the sampling bias problem, and then the third one is data snooping problem. I want to draw your attention to 2 very useful references for today's lecture. The first reference is the Learning from Data textbook, chapter number 5. The other one is a lecture slide from Stanford University, CS 229. Let me jump into the first part of today's lecture, which is how are we going to debug a machine learning algorithm when you see problems. Suppose you have built a logistic regression model. And by that, I really mean that you have solved the following optimization problem. Here is your logistic regression loss. Xn is your input data. Yn is the label. L is the loss function that you're choosing. And then lambda times the 2 norm of the theta, that is the regularization. Suppose you have solved this optimization problem and you try to test the solution of this optimization problem using some kind of testing data set. And unfortunately, when you try to test it, you get an extremely large testing error. So you ask, what can you do to fix this problem? So when you think about this problem, you will try to think that there might be several reasons that can cause my testing error to be big. And here are a list of common wisdom that people may suggest you to consider. Now, this list of suggestions, they are not exhaustive, but I still want to go over them to convince you that these are the possible ways to tackle the problem. The first suggestion is that we may want to use more training samples. Now, I don't know what situations that you are running into, but perhaps that in your data set, you do not have enough training samples. And therefore, by increasing the number of samples, you might be able to train your logistic regression model better, and therefore, you will be able to get a lower generalization error. That could be one possibility. The other possibility is that you may just have too many features in your model. For example, you're using 10,000 features that they are really just coming out directly from your input image. You treat each pixel as a feature. Maybe that's too much for your logistic regression algorithm to fit well. And therefore, in this case, you may want to consider reducing the number of features. Now, the third possibility is that you may not run into the overfitting problem as what I have just described. You might end up having an underfitting problem that can also lead to the high testing error. If that is the case, then you may want to consider using a larger set of features. You can also consider using a different set of features. In the deep neural network setting, that means you can change the network architecture so that the latent representations pulled by the neural network becomes different. Now, these are the questions about your model. You can also ask questions about the optimization algorithm. In this case, we can ask, is it a problem of your stochastic gradient descent? Perhaps you may want to use more iterations. Now you can also ask, maybe it's because I'm using a first order method and therefore I'm not converging fast enough. Maybe I want to consider using a second order method. You can also ask, maybe it's because I'm choosing a wrong lambda and therefore I am underfitting or overfitting. And so I may want to choose a different lambda so that I can improve my regularization. You can also say that perhaps I should choose a support vector machine rather than using the logistic regression because I just know that the support vector machine is more reliable for the data set that I'm using. So given all these possibilities, which one should you consider first? Now, certainly you can say that I'm going to run through my test for all these A suggestions. But if you have limited amount of time, which one should you tackle first? Is there a principle that we can tackle these problems? So in the following slides, I want to introduce two sets of methods that can help us analyze these problems. The first set of techniques is based on the bias and variance analysis, and then the second set of techniques will be used to analyze the optimization problems. Let us first talk about the bias and variance case. The technique that we are using is to inspect the bias and variance of your learning algorithm. There are two suspects in this problem. One is the underfitting problem, the other one is the overfitting problem. And so what you can do in this case is try to analyze the bias and also the variance associated with the data set and also your learning algorithm. Let me illustrate the idea using two figures. The first figure shows you the in-sample error and the out-sample error of your learning algorithm. And here is your desired performance. Now, if you plot the in-sample error and out-sample error as a function of number of training samples, you will be able to see that there is a gap between the two. This may or may not happen, but if it really happens, then you will have two observations. Number one is that in-sample error is approaching to the desired performance. However, your out-sample error has a gap from the in-sample error. So what this means is that your training has been done very well. However, when you try to generalize, it does not generalize well. In this gap, as you recall from our discussion, this is really the variance in the bias and variance analysis. And in order to reduce the variance, what you can do is to increase the number of training samples, or you can try to reduce the model capacity. It is possible to get another set of curves like the one I'm showing you here. Suppose that the desired performance is down here, and then you train your model with your data set. Your in-sample error approaches to this point, and it sort of converge with the out-sample error. In this case, you observe that the in-sample error is actually not good. That means even for the training set, that you are not fitting very well. And therefore, what that can imply is that your model is not complex enough, and therefore you may want to consider using more features or using a more complicated model. So this gives you a very rough outline of how this bias and variance analysis can help you run a diagnostic on this problem. At least for the thing that we have been considering, you can use the bias and variance analysis to pinpoint the issue of having a high variance. This could correspond to the solution of using more training samples or using a smaller set of features, because it could be that you are overfitting. You can also be underfitting the data sets. That means you have a high bias. And in order to solve this set of problems, then you can try to use a larger set of features, or you can try to change a different set of features. Now, this is all about the data sets and also your model. We can also ask the question about the optimization behavior of your learning algorithm. So to understand this situation, let me give you the following example. Here is the optimization problem. Suppose you have trained a logistic model, and then you have trained a support vector machine model. And then you are defining L to be the logistic training loss, okay? And therefore, if you apply theta L to this L, you are going to work well. However, if you apply theta S to this L, you're not going to work well, because there is a mismatch between your support vector machine solution and also your logistic training loss. I'm also defining the outsample error that does not depend on the particular model. I'm only going to evaluate this outsample error by plugging in the model parameters. So this first situation that we want to analyze is this. Your outsample error for your support vector machine is lower than the outsample error of your logistic regression. Now, this should be expected because support vector machine in many cases is more powerful learning algorithm than the logistic regression. So we should expect this to happen. Now, surprisingly, what you observe is that when you plug in your support vector machine solution to the logistic loss, this is actually lower than when you plug in the logistic solution into the logistic loss. Now, I'm not saying that this should happen. I'm just saying that what if this indeed happens? If this happens, what is the implication? In fact, if this happens, what you can really conclude is that you have not optimized well. Why? Because in principle, this theta L should really minimize your logistic loss. And so in any case, when you apply the logistic loss to the logistic solution, it has to be lower than any other solution, including the support vector machine solution applied to the logistic loss. Now, I'm not saying that having L of theta L lower than L of theta S would imply that the generalization error or the outsample error of the logistic solution would be better. I'm just saying that this is the training. This is the training. You should train better with the logistic regression loss and also the logistic regression solution. And so there's something wrong with your optimization problem. It should be something wrong with your optimization algorithm because you have not converged to a solution yet. And therefore, you need to go back to the gradient descent algorithm and see if you have ever converged to the true solution. Now, the second possibility is this. You have the outsample error of the support vector machine lower than the outsample error of the logistic regression. But you also see that the training loss of the support vector machine is just slightly higher than the loss of the logistic solution. So what can go wrong is that your regularization is either too strong or too weak, so that your logistic regression solution is not that good. So what you can do is that you may want to adjust your lambda. And this is the problem of your optimization problem because you have not defined a problem appropriately. So these two advices can help you pinpoint the issues about your optimization algorithm. The first two talks about the convergence. You may want to use the gradient descent. You may want to use Newton's method because you want to get to the solution faster. If you fix the lambda, if you change to a support vector machine rather than using a logistic regression, then you're essentially changing the optimization problem. This can also help in certain cases. Now, I also want to give you some general approach when you try to train a model. There are two typical approaches when you try to train a model. The first approach is what we call the by design approach. It means that you are going to design your model, you build everything from scratch. And in this case, you will also engineer your own set of features and you will implement it and hope that it works. The alternative approach is what we call the build and fix approach. In this approach, what you can do is to go to any website, for example, the GitHub website, and download a piece of code, and you try to implement something quick and dirty. And then you run diagnostics, and then you try to fix and run. Now, these two approaches, they can be used in different situations. The first design approach is better fit when you have a novel problem, that you really have the domain expertise about what you have in hand and what you know about the problem. And therefore, you know that this set of features will work, and you know that from the past experience, this learning algorithm will work, and you also know that this amount of training data should give you some decent results. If that is the case, you may want to consider using a design approach. But in other situations, for example, you are improving on top of certain existing methods, then you may want to really start with an existing architecture and download that and modify that instead of building everything from scratch. So these two approaches really depends on what kind of problem that you are working with. There are other tricks. For example, the notion of ablation study. This is very useful to try to understand which component is more influential than the other components. And so the idea is to cover up one component and keep everything constant, and then you see what is the influence of that component. You may also want to consider using a baseline model and try to warm start your training using this baseline model. For example, if you try to train a ResNet 50, it is better to start with the ImageNet dataset than training everything from scratch, although the dataset that you're working with may not be the same as ImageNet. In many cases, I would advise you try to make things work first. The danger of doing machine learning problems is that you may over theorizing the problem. And often the case is that you may want to make something work first. And then if it works, then you want to go back and do the improvement and also develop your theory. So that concludes the first half of this lecture. In the second half of this lecture, I'm going to give you 3 pieces of advices when you're trying to do a machine learning problem.